Welcome to the deep dive. Today we're looking at something pretty fundamental in AI coding. Large language models are great at spitting out functions, maybe even a single file. But getting them to generate a whole complex software repository from scratch, that's the big hurdle right now.
It really is. If you tried asking an LLM to, say, build a complete data analysis library, you hit this wall. There's just this huge gap between that high-level request and the messy reality of thousands of lines of code, all tangled up with dependencies.
Right. That complexity seems to be where current planning methods just fall apart.
Exactly. And that's why today we're diving into a really interesting structured solution presented in the research, the repository planning graph, or RPG.
RPG. Okay, so this is like a blueprint.
Yeah.
Something more solid than just text instructions.
Precisely. It's an explicit, structured map that the AI can build and evolve. And we'll be looking at the framework that uses it, called ZeroRepo, and how it stacks up on a new benchmark, RepoCraft, which is designed specifically for this large-scale task.
So the goal here is to give you a clear path to understanding how we're moving AI code generation beyond simple snippets towards, well, building real large software systems. It's about tackling that long horizon planning problem.
And a key part of that is moving away from relying purely on natural language for the planning steps.
Okay, let's dig into that first. Why did natural language planning fail here? We've seen attempts, right? Like multi-agent setups, staged approaches.
Yeah, several paradigms. Distributed planning, staged planning, even iterative planning methods. But they all kind of shared the same Achilles heel. They use natural language as the intermediate plan.
And the problem with using just text is,
Well, natural language is inherently a bit fuzzy, isn't it? It's ambiguous, it lacks clear structure or hierarchy, and it's just not robust enough when you're planning something complex over many, many steps. Think hundreds of implementation decisions.
so it gets lost. The plan degrades over time.
That's a good way to put it. The fragility over that long horizon leads to two main failure modes you see in practice. First, there's unstable proposal-level planning.
Meaning it can't even decide what to build consistently.
Right. The functionalities it plans might be incomplete or they overlap weirdly. It doesn't systematically cover everything the user actually asked for in the final repository. You might get 3 ways to load a CSV, but nothing for databases, like you mentioned earlier.
Lacking that high-level architectural view. Okay, what's the second failure mode?
That one's maybe even worse. Fragmented implementation level planning. This is where the architecture itself starts drifting during generation.
Drifting.
Yeah, the way specific functions are implemented changes from one iteration to the next. This causes chaos with dependencies, how data flows between parts, where the module boundaries should be. The whole thing becomes internally inconsistent, even if individual code snippets look okay in isolation.
It sounds like trying to build a house where the blueprint keeps changing depending on which room you just finished painting.
That's a perfect analogy. There's no persistent global structure it's referring back to. And that is exactly why the research introduced the repository planning graph, the RPG.
To be that persistent, structured blueprint.
Correct. It unifies both the high-level what are we building, part the proposal, and the low-level how do the pieces fit together, part the implementation into one single structured graph that can evolve. It replaces that free-form, fragile text plan.
Okay, so this graph structure is the core idea. Let's break down the RPG itself. How does it actually encode the plan? Starting with the nodes, the points in the graph.
The nodes are interesting because they carry this dual meaning. On one hand, they represent functionality capabilities like data loading, algorithm execution, result evaluation. These can be broken down hierarchically, so data loading might break down into load CSV, load JSON, etc.
So that's the what?
Right. And simultaneously, the nodes represent structure. They map directly onto the repository's file organization. A high-level node might be a whole code region, intermediate nodes could be specific files, and the leaf nodes often map to individual functions or classes within those files.
Ah, I see. So a single node tells the AI what function is needed and where it should live in the final file structure. That seems like it would directly combat that architectural drift problem we talked about.
It's designed to do exactly that. Then you have the edges, the connections between these nodes. They define the dependencies and the execution order.
Crucial for making sure things are built in the right sequence. What kinds of edges are there?
There are primarily 2 types shown in the research. First, intermodule edges. These are the high-level connections showing data flow between major components. Like the output from your data loading module needs to feed into the ML algorithms module.
The big picture dependencies.
Then you have intermodule edges.
Yeah.
These capture the finer-grained order within a module or even within a file. For example, ensuring that a file defining some utility functions is generated before the file that actually uses them.
Got it. And these edges, working together, enforce what's called a topological order when you traverse the graph.
Yes, exactly. Traversing the RPG in topological order is key for the generation phase.
And for listeners maybe not familiar with graph theory, what does that guarantee?
It guarantees coherence. It ensures that any piece of code, any function or component, is only generated after all the things it depends on its prerequisites have already been generated and are available. You build the foundation before the walls. It prevents those trying to call something that doesn't exist yet errors.
Makes complete sense. Okay, so that's the RPG structure. Now, how does the ZeroRepo framework actually build this graph? The sources mention 3 stages.
Right. It starts with proposal-level construction. This is about figuring out the high-level features. And to make this more stable than just asking the LLM, ZeroRepo grounds this process in a huge external knowledge base, a feature tree ontology with over 1.5 million known software capabilities.
Whoa, 1.5 million. How does it avoid getting lost in that? How does it pick the right capabilities for a specific project?
Good question. It uses a smart search strategy described as explore-exploit. The exploit part focuses on finding features that precisely match the user's request. The explore part ensures it doesn't get stuck in one narrow area, pushing it to find relevant but perhaps less obvious capabilities from the ontology.
So, precision and diversity.
Exactly. These selected features are then organized into an initial modular functionality graph. That's the seed for the full RPG.
Okay, seed planted. Stage 2 is implementation-level refinement. This sounds like where the abstract plan gets fleshed out into concrete code structure.
That's right. The functionality graph gets enriched into the full RPG. This involves things like file structure and coding, basically deciding which parts of the graph belong in which folders and files, maybe assigning a whole subgraph to a strtls directory.
Mapping functions to file paths.
And also, crucially, data flow and functions encoding. This adds details like typed inputs and outputs for functions, making the data flow explicit. It also looks for recurring patterns.
Recurring patterns, like design patterns.
Sort of. It abstracts common software structures into what they call design anchors. For instance, if it sees needs for load.json and load.csv, it might group them into a single data loader class interface. Or it might identify the need for a standard base class, like a base estimator if you're building something like scikit-learn. It helps enforce consistency and good design.
So it's building not just code, but idiomatic, well-structured code based on recognized patterns. Okay, now the RPG is structured, ordered. Stage 3, graph-guided code generation. How does the graph actively help the LLM agent write the code?
Well, as we said, the generation follows that topological order from the graph, ensuring dependencies are met. ZeroRepo also incorporates test-driven development TDD principles here. But a really interesting side benefit highlighted was how much more efficient the LLM agent becomes.
The localization efficiency. Because it has the map, it doesn't get lost looking for things.
Exactly. The RPG provides that global structure. The agent doesn't have to guess or search inefficiently through thousands of lines of code to find where to add a feature or fix a bug. The research reported that using the graph guidance cut down the effort needed to locate the right code spot, the localization effort, by 30 to 50%.
Wow, 30–50% reduction in just finding where to work. That's significant.
It really is. It speeds up the whole iterative development and debugging process.
Okay, the framework sounds solid, the graph structure makes sense. But the big question is always, does it actually scale? Does it work for big projects? That leads us to the RepoCraft benchmark.
Right. RepoCraft was designed to be tough. It's not about generating small scripts. It uses 6 large real-world Python projects as templates, things inspired by giants like pandas and scikit-learn, but paraphrased, like TableKit or MLKitby. And it includes over 1,000 evaluation tasks that require building these entire repositories from the ground up.
And the metrics were focused on real-world utility, right? Not just code similarity.
Yes. Key metrics were functionality coverage, did build all the needed types of features, functionality accuracy, measured by pass rate on ground truth tests, and just the sheer scale, looking at lines of code, LOC.
Let's talk results, because the numbers comparing ZeroRepo with RPG to baseline methods seem pretty dramatic.
They really highlight the advantage of the structured graph. In terms of scale, ZeroRepo using one of the models, Qwen3 Coder, generated repositories averaging almost 36,000 lines of code.
36,000 LOC. How does that compare?
It's huge. It's about 3.9 times larger than the best-performing natural language baseline, which used Claude Code, and roughly 64 times larger than other baselines they tested.
64 times. So those other methods were essentially hitting a wall very, very early on.
Absolutely stalling out. Whereas the RPG-guided approach could keep building consistently, and crucially, this scale came with correctness.
Right. Size isn't everything if the code doesn't work.
Exactly. Using another model, O3 Mini, ZeroRepo achieved 81.5% functional coverage and a 69.7% pass rate on the tests. Comparing that to the Claude Code baseline, ZeroRepo was ahead by 27.3 percentage points on coverage and 35.8 percentage points on pass rate.
Significant margins. It's building much bigger and much more correct repositories.
The structure enables both complexity and coherence.
But the real killer test for this RPG idea is that long horizon planning. What happens over many iterations? Does the RPG prevent that decay we talked about with natural language plans?
This is probably the most compelling visual from the research. When they tracked performance over 30 planning iterations, ZeroRepo, guided by the RPG, showed near linear growth.
Linear growth in what?
In both the number of planned features, it passed 1,100 distinct leaf features, and in the repository size, exceeding 30,000 lines of code within those 30 iterations. The graph structure maintained architectural integrity, allowing it to keep adding complexity without collapsing.
And the natural language baselines, what did their growth curve look like?
That's the stark contrast. They showed very limited scalability. They just stalled. The best one, Claude Code, essentially plateaued around 3,000 to 4,000 lines of code. It couldn't maintain coherence beyond that point.
Why? Because the text plan just became too messy.
Pretty much. The accumulated inconsistencies and ambiguities in the natural language plan essentially broke the generation process. The RPG avoids that structural decay.
So wrapping up this deep dive, the takeaway seems clear. The repository planning graph offers that missing piece, a persistent, structured foundation that LLMs needed to tackle large-scale software generation.
Yes, it allows them to move beyond just generating isolated bits of code. It helps capture those complex dependencies and maintain coherence over the long haul, which is essential for building real-world repositories.
And it's not just about replicating existing structures, right? There was a final point about novelty.
Right. The analysis also showed that ZeroRepo, using the RPG, wasn't just good at rebuilding known structures. It could also introduce new coherent functionalities that fit within the domain. They measure it up to a 13.6% novelty rate in some tasks, suggesting it can synthesize genuinely new working code structures within the planned architecture.
So it's both stable replication and coherent innovation. That jump from fragile text plans to robust graph plans feels like it genuinely opens up a new level for what automated software development might achieve.
It certainly seems to point in that direction, a much more scalable future.
A fascinating look at structuring AI's approach to coding. Thanks for walking us through that.